Hi, everyone. Thanks for having me. So I'm going to tell you about some more spectral graph theory. But at the end of the talk, you might complain that this doesn't actually look very spectral because I'm not actually going to talk about eigenvalues at all. I'm just going to talk about how you can understand graphs linear algebraically. But it'll be helpful to so there are a lot of, so I'll talk about, over the course of this talk, I'll talk about a few techniques for solving graph problems. But just to be a little bit more concrete, let's just focus on a problem that many of you have probably already seen before, the max flow problem. And we're just going to apply all of these techniques to this max flow problem, just to see how things work. So for those of you who haven't seen what the max flow problem is, here's just let me just informally tell you what it is. So I give you a graph. It can be directed or undirected. For most of the talk, I'm going to actually just talk about undirected graphs. But let's just let me just define it for directed graphs. So I give you a directed graph. Each edge has some capacity on it, some positive number on it. And the goal is to route as much flow as possible from some vertex S to another vertex T without violating any of the edge capacities. So let's just start with the most classical algorithm for this problem, the Ford-Fulkerson algorithm. It dates back to the 50s. So the algorithm is very simple. You have two vertices S and T. You just want to route flow from S to T one path at a time. So just start by picking a path and route flow from S to T along that path. You want to record the fact that and then once you've routed this flow, you want to record the fact that you've routed the flow. And it turns out that in a unit capacity graph, you can do that just by reversing the edges. So you pick a path, record the fact that you pushed flow along it. You pick another path, you push flow along that. Pick another path, push flow along that. Do this for the last path. And then eventually you get stuck. You notice that there are no more, it's not possible to route any more units of flow. And then you're done. You found the max flow. And in particular, the max flow is certified by a minimum cut. So in particular, in this graph, the max flow value and the minimum cut value are 4. And so now we have an algorithm. Let's talk about its runtime. So if f is the maximum flow value, each iteration takes, you use, say, a BFS to find the path. It takes order m time to do each iteration. There are f iterations. So that's an order mf time algorithm. OK, so Ford-Fulkerson is an order mf time algorithm. So that might seem kind of bad because f can be very high in general. So we'd really like to shave off that f. So one thing, just looking at that algorithm, one thing that might seem kind of silly about it is that we're only routing flow along one path at a time. If you could imagine a case where if you have a bunch of paths that don't interact, you could simultaneously push flow along all of those paths. And that's the idea behind a blocking flow. So instead of picking one path at a time, we're going to pick a whole bunch of paths. And specifically, we're going to pick a maximal collection of shortest paths from S to T. So essentially, in each iteration, what we'll do is we'll augment flow along along shortest paths. So for example, we'll start by augmenting flow along that path. And then after we do that, after reversing all of the edges, we can then, the new shortest paths are these two paths. So we augment flow along both of those. And then finally, there's one remaining. The shortest path is just this path. And then after doing that, again, we've realized that the max flow value is 4. But we've done this more quickly. We've done this in 3 iterations rather than 4. So that's nice. So we've saved a little bit of effort. But what happens in general? Can we actually analyze this in a way that gives us a sub-MF time algorithm? And it turns out that you can. And to do that, it's going to be helpful to dig into some graph structure. What about the graph is allowing us to do better in this algorithm? Well, there's one nice thing about this algorithm, which is that after each blocking flow operation, you increase the distance between S and T. So in particular, and now there's a very nice property, which is that there's a trade-off between cuts and distances. So in particular, you can show that if two vertices are at least distance d apart, there is a small cut separating them. There's a cut with size at most m over d. And to see it's not too hard to see this, because so what you do is you just lay out the distances. You lay out vertices by their distance from S. And all of the distance cuts, all of the cuts separating vertices with distance less than I from those greater than I are disjoint. So in particular, one of these cuts is small. One of these cuts must have size at most m over d. That means that the max flow value is at most m over d. So in particular, if blocking flow has taken d iterations up to this point, there can be at most m over d iterations left. So therefore, blocking flow takes, so each iteration takes order m time. And the number of iterations is d plus m over d. Is at most d plus m over d for any value d. So in particular, if we let d be m to the 1/2, the number of we get a bound of m to the 1/2. So the number of iterations is at most m to the 1/2. So in particular, we get an m to the 3/2 algorithm using blocking flow. So the punchline here is that by exploiting graph structure, this relationship between distance and cut size, we were able to get a faster max flow algorithm. Any questions about this so far? Yeah.
Are these optimal in some sense? Are they approximations?
So this is an exact algorithm, yeah. Yeah, so it produces the exact algorithm, but later on I'll talk about some approximate algorithms, yeah. Yeah, so we can actually, so the key phenomenon here, the graph theoretic phenomenon, was that if two vertices are far apart, there's a small cut. And it turns out that we can generalize this. So in particular, to get a provable graph partitioning result. So in particular, so given a graph, you can cluster it into some number of clusters such that the diameter of each cluster is at most r, and the number of edges between clusters is small, is at most m over r. So basically, this has the same flavor of the guarantee that we had before. There's a trade-off between the diameter of clusters and the number of edges between clusters. Okay, so far we haven't seen any matrices or spectral anything yet, so you might be complaining already. But now we're going to do a little bit of linear algebra. So in particular, we like to do better than m to the 3/2. So to do that, let's start by viewing max flow as a linear algebraic problem. And for the rest of the talk, I'm going to focus on undirected graphs. So the capacity going one way is the same as the capacity going the other way. So let M be an n by n matrix, a vertex by edge matrix that takes an m-dimensional vector of flow. So you can write the flow on all of the edges in the graph as a vector. And let M be the matrix that takes a flow vector to the induced demand on each vertex. So for example, let's say that this black vertex has this amount of flow incoming to it. So M would take this flow vector and output 6. The coordinate for the black vertex would be 6. So it just, for each vertex, it writes down the net flow on that vertex. I'll let chi-st be the indicator vector of the pair st. So it has 1 on s, -1 on t, and 0 everywhere else. So now that we have this notation, we can write the max flow problem a little bit differently. The max flow problem is just find a value of alpha for which there is a vector with mf equals alpha times the indicator vector that respects the capacities. But an easier way of writing this down, so if you scale this down a little bit, this problem ends up being just find the minimum norm flow. So basically, the problem is find a vector f in the flow space with minimum L infinity norm, minimum maximum entry. So that's nice. So max flow is just a minimum point problem in an affine space. Let's think about other graph theoretic objects and see how they relate to this. So it turns out that the L1 minimizing flow between two vertices is the shortest path between those vertices. So as I already discussed, the L infinity minimizing flow is proportional to the max flow. And it turns out that the L2 minimizing flow is an object that that you might not think that you know, but you actually do. It's just the electrical flow. So just what I mean by an electrical flow is just the electrical flow between two vertices S and T is just you hook up a battery to S and T, and you see how 1 unit of current would flow from S to T in this graph. And the really nice thing about these flows is that they can be solved or they can be found in nearly linear time. And the reason they can be found in linear time is to find an electrical flow, you just have to solve a linear system. In particular, just a specific type of linear system, the Laplacian linear system. So you just have to solve something of the form Lx equals b. Erasmus will talk a lot more about this tomorrow, and you saw a little bit of Laplacians earlier from Jared and Nick. Okay, so now we have this primitive, we have this hammer, let's bang some nails with it. Specifically, let's try to solve max flow using electrical flows. So let's just try writing down sort of the most naive algorithm possible for solving this problem. One way you could solve max flow is as follows. So just on every edge, just initialize the resistance of that edge arbitrarily, say to 1. And then compute an electrical flow between S and T. So if all of the edges are below capacity, then we're happy. We found a low congestion flow. Otherwise, if you do have an edge that's over capacity, let's try to bias flow away from that edge by just increasing its resistance a little bit. So this algorithm might seem very naive or maybe not, it might seem a little bit hacky, but it turns out that there's a similar algorithm that you can analyze. And in particular, you can fairly easily get an m to the 3/2 time algorithm out of this. So the reason you get something like that is as follows. So basically, the nice thing about writing max flow in a linear algebraic way is that now we can think about the problem geometrically. So in particular, the kind of geometry that's going on is, so recall that electrical flow is finding an L2 minimizing flow. A max flow is finding an L infinity minimizing flow. And basically the maximum ratio between the L2 and L infinity norm of a vector plays a key role in bounding the runtime. In particular, this gap ends up coming in to give us an algorithm that takes square root of m iterations. And each iteration takes order m time because it's just one electrical flow computation. So the total runtime is m to the 3/2. And it turns out that you can actually do something slightly better. You can get an m to the 4/3 time algorithm essentially by when your L2 norm is very far from the L infinity norm, there's a way of essentially deleting. You can find an edge to delete that makes it so that the norms are closer. But anyways, so the geometry here is very important for bounding the runtime of this algorithm. And if we wanted to get a better algorithm, we can also think about things geometrically. Maybe we could possibly get a better algorithm by using some norm that, finding some flow that is more closely related to L infinity norm minimizing flows. And it turns out that you can actually find such a flow efficiently using graph embeddings. So up to this point, I've been talking about things, or earlier in the talk, I discussed graph partitioning. But in some sense, graph partitioning is a little limited in the sense that we're not modifying the graph at all. We're just taking our graph and we're just playing with that graph directly. We're chopping it up. But you could apply something more approximate as well. So in particular, like given a graph G, you could try to approximate it with some other graph H. Of course, there's the question of what kinds of approximations do we actually care about. Well, it turns out that basically this geometry, the L infinity norm geometry, ends up motivating some metric that you would care about. But at the end of the day, it ends up being that you want to basically embed your original graph into, say, a tree or some simpler graph for which the cuts or, say, distances in this original graph are similar or approximately the same as they were in the original graph. So for example, if we could talk about embedding this graph into this tree, try to approximate this graph by this tree. And in this graph, the distance between these two vertices blew up by a factor of 5. So essentially, unfortunately, there are graphs for which this embedding into a single graph doesn't work very well, in the sense that, like, given a graph, embedding it into a single tree can really distort distances. So for example, if you have a cycle graph, all spanning trees of a cycle are just paths that leave out one edge. So basically the distance between the endpoints of that edge are going to be really distorted in some particular spanning tree. But that might seem a little bit silly because all of the other edges are fine. None of the other edges are distorted. So what you sort of wish you could do is you wish you could just average over a bunch of spanning trees rather than just a single spanning tree. And it turns out that you can show a general result of this form that given a graph G, you can embed it into a distribution over spanning trees in a way that only distorts distances by a factor of log n. And if you generalize these techniques quite a bit, it turns out that you can use them for max flow as well. So you can use these techniques to give approximate max flows in almost linear time. Okay, so just to summarize, throughout this talk, we've been trying to understand various techniques in graph algorithms by hammering away at the max flow problem. And we sort of started with a standard approach that doesn't use that much graph structure, this Ford-Fulkerson algorithm. We then talked about how using some graph partitioning guarantees, we could get a faster algorithm. And then we did even better by switching to electrical flows. By writing our problem linear algebraically, we were able to get faster algorithms for this problem, essentially by observing that we can now view this problem geometrically. Any questions? Yep.
This fast approximation, is that only what you're doing normalization, like on a map line?
Yeah, exactly, yeah.
Does that work, like, if you're in a polygon or in a half space or something like that? Like, if you've got inequality constraints, not inequality constraints?
Yeah, so it...
Can you repeat the question?
Yeah, so the question is, so what I'm talking about in this talk is you're doing norm minimization over an affine space. But you could also ask if we can do norm minimization over a polytope efficiently. And so using what I just stated, it doesn't really work. But so one instance of what you're suggesting is directed max flow. So what I talked about in this talk was mostly undirected max flow, but directed max flow is an example of what you're suggesting because essentially you have a bunch of constraints that say that the flow on an edge must be positive. And so it turns out that there has been a lot of work recently on getting faster max flow algorithms using electrical flows. And those usually use things like interior point methods. Yeah. And Rasmus will talk a little bit more about them tomorrow, I think. Yeah.